Hi again, welcome to the course on risk modeling in insurance. With your background from the discussion of the Poisson distribution, you will now move from a standard count distribution, like the Poisson, to a mixture of count distributions. Now, studying such mixtures is relevant as they will equip you with more flexible distributions to model count data. And you will start with discrete mixtures for count data. In a discrete mixture, you're going to express the probability function with a set of parameters psi, consisting of weights q1 up to q nu on the one hand, and distribution-specific parameters xi1 up to xi nu. So that is a lot to digest, isn't it? Well, what I mean here is that the probability function is constructed starting from new other probability functions, p1 up to p nu, each with their own set of parameters, xi1 up to xi nu. And we'll put these probability functions together by giving each of them a certain weight and adding them up. Now the q's are so-called mixing weights, so they take values between 0 and 1 and they sum up to 1. And these conditions are necessary to guarantee that the probability function constructed as such is again a well-defined probability function. That is, it will take values between 0 and 1, and when summing all probabilities, you should get 1 again. Now it is an exercise for you to verify that this is indeed correct with the construction as formulated here on the sheet. Now a first popular example of a discrete mixture is the so-called zero-inflated Poisson distribution. As its name suggests, you start here from a standard Poisson distribution. You will inflate the probability mass at 0 and get a new count distribution. So the first building block in this two-component discrete mixture is a degenerate distribution, denoted here as P1, where all the probability mass is put at 0. And the second building block in this construction is a regular Poisson distribution, denoted here as P2. And in this zero-inflated Poisson construction, we're going to mix both distributions. Now let Q1 and 1 minus Q, let Q and 1 minus Q be the mixing weights. Then the probabilities in this two-component mixture are given as follows. Well, first, consider the probability that the random variable n takes the value 0. Now, outcome 0 is possible in both components of the mixture. So that is the degenerate distribution P1 as well as the Poisson distribution P2. Hence, you rewrite the probability that n equals 0 using the law of total probability, where the notation n wiggle P1 is short for n follows distribution P1, and similar for the expression with P2. Now, when n follows the degenerate distribution P1, the probability to observe outcome 0 is 1. But when n follows the distribution P2, that's the Poisson, the probability to observe a 0 outcome is given as the corresponding probability from a Poisson distribution with parameter lambda, and that is the exponential of minus lambda. Combine this with the weight attached to each component in the mixture, and you find the probability in the zero-inflated Poisson of a 0 outcome. Now, with a completely similar reasoning, you will also find the probability of a non-zero outcome, k, in this Poisson mixture. When k is non-zero, the degenerate component has no probability mass at k, and the probability function of the Poisson evaluated in k takes the usual expression, so that's the exponential of minus lambda times lambda to the power k divided by k factorial. Combine these with the respective weights, and you find the probability function of the zero-inflated Poisson evaluated in an outcome k that is different from 0. Now, it is insightful to convince yourself that this construction actually leads to a well-defined probability function. Here too, the probability function should take values between 0 and 1, and the probabilities should add up to 1. So let's see how that works. Well, we sum the probability that n takes a value k over all possible outcomes k. We distinguish between the probability at 0 and the probability of non-zero outcomes. We rearrange, and we're going to use the fact that in the Poisson distribution with parameter lambda, the probabilities add up to 1. So here you see why these mixing weights, in this case q and 1 minus q, why they should add up to 1 to ensure that the probabilities in the mixture distribution add up to 1. Now, why would you opt for such a zero-inflated Poisson distribution instead of a regular Poisson distribution? Well, count data often show an excess of zeros against the Poisson distribution, and that is particularly true in an insurance context, since the event of interest, claiming, getting involved in an accident, and so on, since the event of interest does not often occur. Now, to accommodate this feature, you can mix any count distribution of your choice with a degenerate distribution at 0, and you will call the resulting mixture a zero-inflated count distribution. So hence, the expressions here on the sheet generalize the construction of the zero-inflated Poisson, where now the distribution P2 can be any count distribution, for example, the negative binomial. Well, next to these discrete mixtures, continuous mixtures are also useful tools to construct more flexible count distributions, starting from basic discrete distributions. In the continuous mixture setting, you let the parameter xi, or the vector of parameters xi, take values from a continuous distribution, here denoted with g. Thus, instead of fixing the parameter at a certain value, the parameter is now a random variable itself and follows a certain distribution. A new probability function, pk, then results by integrating over all possible values that the parameter xi can take. This is the general recipe for the construction of a continuous mixture. Now, in the Poisson setting, the continuous mixture construction often appears in the following format. You multiply the parameter lambda in the Poisson distribution with a positive random effect theta. So theta here is a random variable. It has to take positive values because you use it in the mean of the Poisson distribution, and the mean of the Poisson distribution has to be positive. Conditional on this theta, the random variable n will follow a Poisson distribution with a parameter lambda times theta. So the idea behind this construction is that not all policyholders in the portfolio have the same mean claim frequency. Some represent higher risks with a value of theta larger than 1, while others represent lower risks. Now, technically, you can look at this construction in two ways, conditional or unconditional. In the conditional construction, you work with a Poisson probability function with a parameter lambda times theta. While unconditionally, you're going to integrate over all possible values of theta. Of course, one can only work out the integral when a specific distribution for the theta here is specified. And we call this construction a mixed Poisson law, denoted here with m point, and then referring to the parameters in this construction, in this case lambda and theta. Now, it is useful, before moving on, to convince yourself that both specifications, the conditional one and the unconditional one, are legitimate PDFs, or legitimate probability functions. So take the expression for the conditional probability function and sum over all possible outcomes k. Using the Taylor series of the exponential function over here will show you that indeed these conditional probabilities add up to 1 as they should. Looking at the unconditional probabilities, you will again sum the probabilities over all possible outcomes, k. And using the result from above, so plugging in the result for the conditional probabilities over here, you see that that the sum indeed again, you see that these conditional probabilities again add up to 1, so that you are left with the integral over all values of theta of the PDF of the random variable theta evaluated in theta. And that of course has to be 1, since this PDF is a legitimate PDF. As a final consideration, regarding the construction of continuous Poisson mixtures, you will now focus on the expected value of this random effect theta. It is convenient in an insurance pricing setting to impose that the expected value of this latent variable theta should equal 1. As such, the unconditional expected value of the count random variable is equal to lambda, and thus that means that on average the mean claim frequency of the portfolio still equals lambda and is not changed. Now you can verify this result in 2 ways. First, you can do the maths explicitly and calculate the expected value of n. That implies that you take the sum of k times the unconditional probability that n equals k, and you're going to sum over all possible outcomes k. Rearranging this expression shows that this leads to lambda times expected value of theta. Now, since theta has expected value equal to 1, this indeed reduces to lambda. On the other hand, you can directly apply the Tower rule, or the law of iterated expectations, and work with conditional expectations, as demonstrated at the bottom of the sheet. Again, you retrieve the value lambda as the overall mean claim frequency. Now, you're going to study one particular example of a continuous Poisson mixture. And here too, you mix the Poisson with a gamma distributed random effect theta. Now, the gamma has support on the positive real line with a density as specified over here. And it uses 2 parameters, alpha and beta in my notation. Mixing the Poisson with a gamma leads to the negative binomial distribution. That's a widely used alternative to the Poisson distribution for count data. And to satisfy the condition that the random variable theta has expected value equal to 1, you're going to choose both parameters in the gamma distribution equal to each other. Under this condition, this gamma distribution has an expected value equal to 1. So let's calculate the unconditional probability that n equals k from this construction. You start from the integral expression for the unconditional probability as formulated earlier. You replace the density of theta with a gamma density, where both parameters equal a. You put the terms that do not depend on theta in front and you work out the integral. You'll need some knowledge of the gamma distribution to see what this integral becomes. So I invite you to work that out yourself. Rearranging terms then gives you the probability function of a negative binomial with parameters lambda and a. Lambda is the mean of this negative binomial distribution, and therefore including information on exposure to risk works in the same way as with the Poisson distribution. You simply replace the lambda with lambda times d, where d is the measured exposure to risk. Putting this all together, you now have a new count distribution at your disposal, the negative binomial. It uses 2 parameters and therefore it has more flexibility than the 1-parameter Poisson distribution. Lambda captures the annual expected claim number and d the exposure to risk, or in the context of a motor insurance, the length of the period of insurance coverage. Do mind the use of the word annual in this sentence. Lambda is the mean of n if the exposure equals 1. So that's why you should label lambda as the annual expected claim frequency. It is the expected claim frequency for somebody who is covered during a full year. To conclude this example, you will derive an expression for the mean and the variance of this negative binomial distribution. So in general, for a mixed Poisson law, you have the following expression for its mean and its variance. And we derived the expression for the mean earlier on in this video, and the expression for the variance is left for you as an exercise. So what you need here is the expression of the mean and the variance of your random variable theta following a gamma distribution. And those are given over here for the general notation where I have two parameters alpha and beta that are not necessarily equal to each other. Doing the necessary plugins, you will find now lambda times d for the mean of the negative binomial distribution and lambda times d plus lambda d squared divided by a for its variance. So you conclude that the variance in this distribution is larger than the mean. So because it's the mean plus something positive. This is a distribution that allows over dispersion. That is, variability in your data can here be larger than the mean of your data. So that concludes the video where we discussed mixtures of Poisson distributions.